Independence vs. mutual exclusivity. Welcome, everyone. Today, we are going to tackle a topic that frequently trips up even the most diligent students in probability theory: the distinction between independent events and mutually exclusive events. Now, as we begin, you might notice that both of these terms are used to describe how two or more events relate to one another. Because they both deal with the relationship between events, it is very easy to accidentally use them interchangeably. However, I want to emphasize right from the start that they refer to entirely different properties. To help you keep them straight, think of it this way. One concept is concerned with whether two events can physically occur at the same time, while the other is concerned with whether the occurrence of one event gives you any new information or clues about the likelihood of the other. Over the next few slides, we are going to break these down mathematically and look at some real-world examples to ensure you never confuse them again. Understanding mutual exclusivity. Now that we've established that independent and mutually exclusive are two very different concepts, let's dive into our first term, mutual exclusivity. You might also hear this referred to as dislamped events. When we talk about mutual exclusivity, we are looking at a property of the events themselves, specifically how they relate to the sample space. That is, the set of all possible outcomes. The simplest way to remember this is that two events are mutually exclusive if they simply cannot occur at the same time. It is an either-or situation. Let's look at the mathematical definition to be precise. If we have two events, let's call them E and F. They are mutually exclusive if their intersection is an empty set. In notation, that is E intersection F equals the empty set symbol. Because there is no overlap between them, it follows logically that the probability of both events occurring simultaneously is exactly 0. In other words, P of E intersection F equals 0. To make this concrete, let's look at a real-world example, tossing a single fair coin. In this experiment, let's define event E as getting a head and event F as getting a tail. If we break this down step by step, we ask ourselves, can a single coin toss result in both a head and a tail at the same time? The answer, of course, is no. Because they can't happen together, the intersection of E and F is empty. This means the probability of E and F happening together is 0. Therefore, we can conclude that events E and F are mutually exclusive. Now, keep this cannot happen together idea in your mind, because in the next slide, we are going to look at independence, which is a completely different way of looking at how events relate to one another. Understanding independence. Now that we have cleared up the concept of mutual exclusivity, where events simply cannot happen at the same time, let's move on to our second major concept, independence. Unlike mutual exclusivity, which is about whether events overlap, independence is a property defined by the probabilities themselves. We say that two events are independent if the occurrence of one event does not affect the probability of the other event occurring. In other words, knowing the outcome of the first event gives you absolutely no new information about the likelihood of the second event. To put this into a mathematical framework, we say that two events, E and F, are independent if the probability of E intersection F, which is the probability of both events happening, is equal to the probability of E multiplied by the probability of F. To make this concrete, let's look at a real-world example involving two separate actions, tossing a coin and rolling a six-sided die. Let's define event E as getting a head on the coin and event F as rolling a 6 on the die. Let's break this down step by step to see if they are independent. First, ask yourself, if I toss the coin and it lands on heads, does that change the likelihood of the die landing on a 6? The answer is no, the die doesn't care what the coin did. Now, let's look at the numbers. The probability of event E, or getting a head, is 1/2. The probability of event F, or rolling a 6, is 1/6. To find the probability of both happening together, the probability of E intersection F, we multiply them. 1/2 times 1/6, which gives us 1/12. Because the probability of both occurring is exactly equal to the product of their individual probabilities, we can officially conclude that events E and F are independent. This leads us to a very important point, which we will explore in the next slide. If these events are independent, can they ever be mutually exclusive? Let's find out. The critical distinction. The most important takeaway you must memorize is that independence and mutual exclusivity are not the same thing. In fact, if we are dealing with events that have a chance of actually happening, meaning their probabilities are greater than zero, these two concepts are actually incompatible. They cannot exist at the same time. Let me explain why independent events cannot be mutually exclusive. If we have two events, let's call them E and F, and they are independent with non-zero probabilities, meaning the probability of E is greater than zero and the probability of F is greater than zero. Then, by definition, the probability of E intersection F, which is the probability of both happening, must equal the probability of E multiplied by the probability of F. Now, think about the math. If you take two positive numbers and multiply them together, your result must also be a positive number greater than zero. Therefore, the probability of the intersection cannot be zero. But, as we learned in our second slide, for events to be mutually exclusive, that intersection probability must be exactly zero. So, you can see the contradiction. They simply cannot be both. Now, let's look at it from the other direction. Why mutually exclusive events cannot be independent. If events E and F are mutually exclusive, we know that the probability of E intersection F is exactly zero. This means that if I tell you that event E has already occurred, the probability of event F occurring instantly drops to zero. Because the occurrence of event E has drastically changed the probability of event F, changing it from its original value down to zero, the events are clearly influencing each other. And if one event influences the other, they are, by definition, dependent. Now, we have looked at the definitions for both concepts, but this next slide is arguably the most critical part of the entire lesson. I want you to pay close attention here, because this is where most students run into trouble during exams. So, as we move into our next slide, keep this logical tension in mind. Mutual exclusivity implies a very strong connection, while independence implies no connection at all. Common mistakes to avoid. First, a very common error is mistaking the idea of events being separate for them being independent. It is tempting to think that if two events are mutually exclusive, meaning they are physically separate and cannot happen together, that they must be independent. However, as we discussed in the previous slide, the exact opposite is true. If two events are mutually exclusive, they are actually highly dependent. Why? Because if I tell you that event E has occurred, you now know for a fact that event F cannot possibly happen. The occurrence of one event has provided you with massive amounts of information about the other, which is the very definition of dependence. Second, please be careful not to confuse your formulas. It is easy to mix these up when you are under pressure. Just keep this distinction clear in your mind. For mutual exclusivity, the probability of E intersection F equals zero. But for independence, the probability of E intersection F equals the probability of E multiplied by the probability of F1 is about the intersection being empty, while the other is about the intersection being a specific product of individual probabilities. Finally, don't forget the importance of non-zero probabilities. The rule we just covered, that independent events cannot be mutually exclusive, is only true if the probability of E and the probability of F are both greater than zero. If one of the events has a probability of zero, the distinction becomes much more subtle. Now, before we wrap up and look at our final summary table, I want to pause and address some common pitfalls. I've seen many students stumble on these specific points during exams, so please pay close attention. Keep these traps in mind, and you'll be well prepared for the final summary on our next slide. Key takeaways. All right, we have reached our final slide, which serves as a summary table to help you consolidate everything we have discussed today. I recommend you take a moment to look at this comparison, as it brings together the definitions, the formulas, and the intuition we've built up through the previous slides. Let's start with the first row, the core concept. This is the fundamental difference. for mutually exclusive events, the key idea is that they simply cannot happen at the same time. On the other hand, for independent events, the focus isn't on whether they can happen together, but rather that the occurrence of one does not affect the probability of the other. Let's start with the first row, the core concept. This is the fundamental difference. For mutually exclusive events, the key idea is that they simply cannot happen at the same time. On the other hand, for independent events, the focus isn't on whether they can happen together, but rather that the occurrence of one does not affect the probability of the other. Now, let's look at the second row, which covers the mathematical condition. This is where you'll want to be careful with your notation during exams. For mutually exclusive events, the probability of E intersection F equals 0. But for independent events, the condition is different. The probability of E intersection F equals the probability of E multiplied by the probability of F. In the third row, we look at the relationship. Notice that mutual exclusivity is a property of the sample space itself. It's about the outcomes. Independence, however, is a property defined by the specific probability values assigned to those outcomes. Finally, let's look at the intuition row. This is my favorite part because it helps you check your logic. If you are dealing with mutually exclusive events, just think, if event E happens, then event F cannot happen. But if you are dealing with independent events, your mindset should be, if event E happens, it tells me absolutely nothing new about the likelihood of event F. If you can keep these 4 rows clear in your mind, you will avoid the common pitfalls we discussed earlier and master this topic. Great job following along today.